Hello and welcome to this talk about developing embedded system with the GRiSP embedded board. In this talk we're going to show you a prototype we made with it, which is a home automation visualization prototype. So I'm Claudia Doppioslash.
And I am Adam Lindberg.
And our company is PERSISTED GmbH. And we do embedded Erlang in general, and also we have specific application for the automotive and industrial automation industries. And one of our products is the thermal flashing HydraProg, which you see up there. And then another application is smart conveyor belts. If you were in the talk before this, in this room, you have probably seen them. And we are also part of a EU project, which is the LightConEdge, and we're going to talk more about that later. So this is a table of contents of this talk. So basically, we are going to explain why we think this is a good example for the GRiSP embedded board, and what is the hardware platform, what is the software stack, and we're going to show you the home automation demo, and then we're going to talk a bit about future developments. So one thing that's usually pretty hard to do with embedded systems is actually to look into them, to visualize and introspect them. They tend to be a bit of a black box, also because they are generally C applications or C++ applications, and they don't have some nice things that Erlang has. So Erlang makes it really easy to put a web service on the embedded device itself. So you can just get your data and then get it to the web server and then get it back to some web application. And then you can also have interactive shells with Erlang. So now we're going to talk about the hardware of the GRiSP board, and Adam is going to do it.
Yeah. So the GRiSP board is a specialized hardware we made for running Erlang. It's for IoT applications, and it's an embedded wireless device. So by embedded we mean like low power, efficient, small, portable. Wireless, because it has built-in Wi-Fi, and you can connect many other types of radio extensions and PMODs and so on. So the board itself has a 300 megahertz ARM processor. It's a Cortex M7. It has 64 megabytes of RAM, which is quite a lot for Erlang. So Erlang in itself is already quite memory efficient. The VM is fairly small, and 64 megabytes gives you lots of space for any type of embedded applications you want to build. It has 2.4 gigahertz Wi-Fi built in, and a microSD slot for deploying software, so you can ship new software to it easily or replace it. So let's look at the board a bit more in detail, what type of hardware we have available. So I'll quickly go through a couple of generic things that we won't mention in this talk, and then I'll go into a bit more depth of the stuff we're actually using for the home automation prototype we've done. So some generic things that might be interesting if you do some embedded IoT things for home automation, maybe we have some switches and LEDs. So switches you could use for hardware things like toggling things on and off or triggering certain events. Or RGB LEDs for showing statuses for various things on the board that you don't need a GUI for. The board has a couple of connectors for various types of hardware. So we have GPIO, UART, and SPI, which are all different types of connectors. Or the connectors are the same, but it's different types of protocols to talk to the hardware, basically. Different levels of abstraction and capabilities. So for home automation, we're going to look at two other connectors a bit more in detail. The first one is I2C. This stands for Inter-Integrated Circuit, and was originally developed in the 80s by Philips. And it is a 4-wire protocol, master-slave protocol. And it has 1 wire for the data, 1 wire for a clock line for synchronization, and power and ground in addition to this. And it is a bus protocol, which means you can chain lots of devices on the same bus, and you can address them. So that means each device has an address, and you can send data to a specific device using their address. And you can have up to 1,000 devices on the same bus, so it's very scalable. It's usually used for board local communication. So by that we mean that over longer distances, it's not so reliable. So you lose speed, you lose transmission quality. So you usually use it for things which are close to the device you're building. So if you have a box with the GRiSP board in one end, you might put some other hardware in there, and you might use I2C to then wire all this up and talk to it. It's fairly slow, so it's about 0.4 megabit per second. Because of these wires and the distance. The other thing we're going to actually show a demo about is one wire. And this is an even more lightweight type of bus. So it's developed by Dallas Semiconductors. And the cool thing, the name comes from it only using one wire plus ground. So it's a small parenthesis there for both the data and the power. So that means that if you have lots of devices on this bus, they can power themselves off the data line when they're not using the data. So each device can have a small capacitor that they power when they're not active or when other devices are active. And then once they get a message that's for their address, they would then start using this capacitor as a temporary battery. So it's very similar to I2C, but the good thing is that it supports longer distances, so it's more stable. And this is more a room scale type of connector. So it's slower than I2C because of this. But if you want to wire up a house or like a bunch of rooms, you can totally do this with wires. And it's an addressable MICROLAN. So each client has an address, just as with I2C. And it's a unique 64-bit address, so it's pretty strong. And it consists of the ID of the device, a unique ID, the type of the device, and a small checksum. So if you have devices showing up on this bus, you can actually already figure out by the ID what type of device it is and start using the right driver to talk to them. And popular examples of devices for one wire is like simple buttons, light buttons, for example, key fobs for security systems, different types of sensors like weather, climate, temperature, and so on. What also useful for home automation is wireless communication. So on the GRiSP board itself, we have built-in Wi-Fi. So there is a Wi-Fi chip. It's a BGN network, 2.4 gigahertz, and it's wired up by an onboard USB interface. And it supports up to like 70 megabit per second for 20 megahertz bandwidth, or up to 150. I mean, this is theoretical Wi-Fi speed, so you never reach them, but it's quite fast, so it's useful for a bit more heavy applications and for integrating with the rest of your home, for example. It also has power saving, so it can go into low power mode, or you can turn it off when you don't need it. So if you want to build a device that sits somewhere, maybe powered by battery, you can still totally use this and then adjust the usage of the Wi-Fi to your needs. And in addition to the built-in Wi-Fi, you can then connect PMODs to this. So I'm going to bring up one example here, which is the PMOD RF2. And it is a PMOD that has a receiver for IEEE 802.15.4, which is a wireless personal area network standard. So it's a wireless standard for making kind of local networks, specifically made for low cost and low power devices. So things that needs to run for a long time, maybe connect to some master every now and then, which then could be the GRiSP board with one such PMOD. And it supports up to around 10-meter range things. And on top of this standard, there are high-level protocols, and two examples are Zigbee, which is an open standard protocol, and MIWI, which is a proprietary one. But lots of devices, they support one of these protocols, for example, and I think this PMOD also has support for using these protocols. So the cool thing is, if you use this PMOD, you talk to it with SPI, the SPI protocol, which we have drivers in the GRiSP runtime. So you do it from Erlang, and then you don't have to deal with all the nasty hardware level details like wireless things. So this is very cool.
So now we're going to talk a bit about the front end and the back end stacks in our software. So the first thing to notice is that this is a real Erlang VM, which is running directly on the CPU. So there's no intermediary there, there's no operating system. And We call it real bare metal because bare metal is a bit of a, overused term. Maybe they refer to bare metal even when it's like a virtualized server in the cloud. So this is actual bare metal. And this is an overview for the software stack of this prototype. As you can see, there is a GRiSP board, there are the sensors, and there is a front end. So the way this works is the GRiSP board has got these sensors connected through the one-wire protocol, and drivers for this, they get information from these sensors, and then they give this information to the web application, which also runs on the GRiSP embedded board. And that application sends this information back to the through the WebSockets to the front-end application. And now we're going to show the front-end application, but first I need to give credit where it's due. Most of the D3 part and the SVG part of this application has been done by Amelia Bellamy-Royds, and she's a published author with O'Reilly, where she has 4 books on SVG, and we asked for her help a while ago with some tricky SVG and CSS stuff, so she also did a lot of this work. And this is the screenshot of the application. As you can see, there are 3 thermometers, and they are components made in D3 and SVG. And then below there is a graph, which is a graph which shows historical data of all the sensors which are connected. So basically, there is a thermometer for each sensor that's going to get connected. And so this is what happens when you connect. So the GRiSP development board has got an IP, and you can connect to it, and there is a web server on it. So this is what you get: a static HTML, and then you get the JavaScript and the CSS, whatever it's on it, and then the components are made in SVG, and D3 is getting the information from the web sockets, and then updating the information into the SVG. And this is a graph of how, so there is a particularity about D3 that it needs to bind with a parent DOM component. Since we are going to add and remove sensors, we don't want to be, tied to a static DOM. So there is a JavaScript controller that creates and removes DOM elements as needed and binds them with D3. And this is the WebSockets protocol. So basically, once you've loaded the static HTML, the WebSockets will open, and then you start to get your data. And this is also an example. The protocol is in JSON, and this is an example of it. As you can see, it's very simple. It just got an ID and a time and a value for each temperature sensor. And every time one temperature sensor updates, it gets an updated snapshot of all the data connected to the system. And then it shows it. And now we're going to talk a bit about the web server.
Yeah. So on the back end, we use Erlang. So we have an Erlang application, and we have COWBOY as a dependency. So we use COWBOY to first just serve the static pages from memory, from the SD card. And then we also set up a WebSocket listener that the web page will connect to back once you load the web page in your browser. And in the Erlang application, we're using the GRiSP runtime to use the drivers. So we have a one-wire driver already in the GRiSP runtime, and we have a high-level Erlang driver for these temperature sensors. And the Erlang application for the prototype for the demo is basically wiring all this together. So it runs a regular scan on the one-wire bus to see if new temperature sensors has showed up. And whenever it finds a new one, it will start an Erlang process that then will regularly query that specific sensor with its own unique ID for the temperature. And then when the WebSocket updates, it will ask all the temperature sensors that are available, like what's your current temperature, and then we'll ship it off to the front end regularly as updates come. So we're going to attempt a demo, and let's see how that goes. So we have a GRiSP board here running out of a battery pack. And we have a long one-wire bus here, a long wire. So we have 3 wires. It's broader than this, but we only use 3 of them because we also power the temperature sensors with onboard power from the GRiSP board. So it means that those sensors, they don't have this fancy capacitor thing because they're just like a super simple temperature sensors with those 3 wires, and we'll just use the power from the GRiSP board for this demo. So could you maybe hold this one, and then I will set up the computer side of things. let me know if it shows up. Okay, there, perfect. So now I'm on the same Wi-Fi as the GRiSP board. And the GRiSP board has booted, and I configured it to connect to this Wi-Fi. I'm on the same Wi-Fi with my laptop. And what I can see here is I can already ping the IP number that the GRiSP board has. So it's running on the Wi-Fi. And let's try to view the web page that it's serving. So this is the dashboard that we have for our prototype. And it's a very simple one. Right now it's empty because we don't have any sensors. We don't even have a one-wire bus, but it's fine. So it's still running, and the backend is like regularly querying the one-wire bus to see if anything is there. So what we'll do is we'll connect this to the GRiSP board. So the one-wire interface has 3 wires, as I said before, 2 or 3, depending on the power. So first the data wire, and then the ground wire, and lastly the power wire. So this means that now the GRiSP has this one-wire bus active, and it will just keep scanning this for things. So if we plug in a temperature sensor into one of these slots, we should see it come up in a short while. So the scan is running every 10, 15 seconds. The reason it's not like snappier than this is because one-wire is actually really slow protocol. And for this demo, we're kind of abusing it. So we're running these things like much faster than you normally would do if you would wire this up in your home, just so we can see some nice things on screen. So normally you would never like run the scan regularly. You would maybe have an interface where you go in, and if you plugged in a new sensor in a new room, you would just go and do it manually, basically. For this demo, we automated it, so it looks a bit more fancy. And now we'll see if we can do like some interactive things. So we want some help from the audience. So basically, if you go and hand out a few of these sensors, and we can actually bring the GRiSP board with us because it's wireless and it has a battery pack. So this should all be possible. And let's see if the thing still works. Maybe you just hold this, and then let's maybe pass this around. So make sure you get like a slot somewhere with a space for a sensor. So maybe give all of them here, and then they just pass it backwards along the wire. And oh, okay. Let's see if I can wake it up. So if you plug one in, you should see them popping up after a while. What you can do, for example, is you can like hold your finger around it or breathe on it or something like this, and you can then see the temperature slowly going up. And here we also have the historical data graph of the temperatures that we've seen so far. So it's a bit slow because I don't want the scan to run too often, because as you put in more sensors, the scan kind of competes with the sensor data, which means that if I was scanning the whole time, there would be no traffic on the wire for actually getting the data and so on. So let's see if we get a few more sensors showing up soon. So how many has been plugged in so far? Okay, so it should be more showing up. Not sure why. Yeah, so one problem is like as soon as you have lots of them on the wire, the scan is very slow. So maybe we added like too many too fast now. Okay, there they go, all of them. And so, I mean, you won't see it now because we didn't add them like regularly, slowly, but the speed of the updates would basically be slower and slower the more sensors we add. So typically in a real world use case, you would have a room or a small house wired up with these sensors, and then you would maybe update them once a minute or once every 5 minutes or something, because you don't need the data that regularly. Now we're just doing it for show, basically, to get some more interesting demos. So what's cool is, right now, we're running an Erlang application on this GRiSP board lying around over there in Paris lab, and it is battery powered, and it has a long kind of sensor with temperatures and things like this. So what we can do is we can also talk to this GRiSP board. So yeah, we see this. So I will attempt to log into the Erlang shell on the GRiSP board. So now we have an interactive Erlang shell running on embedded hardware over there. And so the way this works is that I'm running a remote shell with Erlang. Is the text okay? Can you see it, or should I make it a bit bigger? Bigger, yeah. Suspected so. So let's see if we can fit most of the stuff in here. So this is the Erlang shell. Even bigger? Okay, let's maybe let's do it like this. So this is the GRiSP shell, and if I do, for example, application, which applications, you can see that we are running COWBOY, for example. We run the GRiSP runtime, and we run this application called Home, which is the one we wrote for the demo that kind of connects all of this together. One other thing we can do is, so I have this GRiSP project that I created on my laptop, and this is where all the code is. So I can start a rebar shell here. And what you can do with rebar is, when you start a rebar shell, you can tell it to set a node name for the Erlang VM that starts, that rebar uses for compilation and things. And I'm setting the same cookie that I'm using on the GRiSP board. So right now, this is just a normal rebar shell running on my local computer. And because I'm on Wi-Fi, and because I've set up the host name to point to the IP number of the GRiSP board, I can then connect to this one. So this is the same node name that's up here. And I get a pong back, which means the ping worked. And if I now check which nodes I'm connected to, you can see I'm connected to the GRiSP node remotely. So this is now distributed Erlang running from my laptop to this GRiSP board. If I check the nodes on the GRiSP board itself, you'll see 3 nodes, because there's a hidden node behind the remote shell node running on my local computer that connects to the GRiSP board as well. And rebar has some fancy functionality for running rebar tasks in the rebar shell. So I just compiled the code in my local computer, and it's running on that local shell only. So with this information, we can then go into an editor. So this is the driver for the temperature sensor in the GRiSP runtime. And it has a few functions to talk to over one wire to the sensor. So the sensors work like this, that you send a convert command. So this is this function here. And that will initiate one temperature conversion and store the value of the thermometer on the device. And then there's a temp command where you actually acquire the value that's stored on the device. So you specifically have to tell the device to update the temperature. You can also configure it to like auto-update, and then you can ask for the temperature. So we do some fancy bit mangling in Erlang. This is really nice because we don't have to do C to do this. We can do everything in Erlang with some binary pattern matching. And this is basically how you get out the 12 bits of temperature value from the sensor data. And because it is in total 2 bytes, 16 bits, so we divide it by 16 in the end when we get the numerical value to actually get the degrees Celsius, because the sensor gives us degrees Celsius. That's how it's made. So if you wanted to change this, for example, to Fahrenheit, we could update the calculation. So I comment out the old one and use a Fahrenheit calculation instead. Now I go here and I compile the application again, which will recompile the GRiSP runtime and the driver. And I can now net load the module, which is one wire. 19B20. And that means I've now loaded the new driver on the GRiSP board. And the next time we get an update for temperature values, we should actually get Fahrenheit values instead. Possibly this might be a little bit slow, so let's see if we can see the actual WebSocket, or maybe the WebSocket died. Console. Let's see. Let's reload the page and see if we can talk to it. So it could be that like it's just super slow acquiring the temperature and we have to wait for a while. If we don't get anything here, I will just try to run it manually on the shell to see that we actually get Fahrenheit. Okay, there we go. And now the values are in Fahrenheit. So I basically live updated the home automation application, I tweaked the code, fixed a bug, and I loaded the new code over the wireless network, and it just works. So this is our demo. Maybe let's just continue from here. Are you fine without the notes for the last slides? Okay. So, kind of updates of what we're working on at the moment, or what's the future for this work and for the GRiSP itself. So, one thing we're looking into is to use MQTT. So, MQTT is a kind of machine-to-machine interface. It's a message queue made specifically for Internet of Things applications. And there is a MQTT smart home initiative that kind of has some architectural best practices and collects lots of projects that use MQTT specifically for a smart home. So the way you would use MQTT is, for example, you would enable MQTT on the GRiSP. You would maybe add some dependency, find or make a library to use this. And then you could connect, so either you run like the GRiSP as the central home hub, which runs an MQTT message queue on it, or you have already one somewhere in your home or on a server somewhere. And then you can talk with MQTT to this hub and publish, subscribe messages, things like this. So for example, one of the applications in this smart home repository, or like one of the applications they list, is a bridge from Apple HomeKit to MQTT, which means if you had MQTT running and you had the GRiSP sending like MQTT events, for example, with these temperature values, you could then view this via Apple HomeKit on your iPhone or something like this. And there's lots of different projects for different hardware and different like GUIs and frontends for things. So this is very cool stuff. And we also plan to use MQTT for some more industrial applications as well, because it's a very nice protocol for distributed systems in general when it comes to automation.
And now we're going to talk a bit about the future for the front-end library. So it would be nice for us to get more of a generic library, as the application you saw was all Haddock based. It was all Haddock basically. But it would be nice to get a more generic library with more types of widgets, so you can get many different types of sensors and still have some widget that you can use to show them off. And it would be also nice to get the dashboard to be editable and persistent, so you can change the layout of your temperature sensors, for example. You can change the layout of your widgets, you can change the type of widgets, you can change their value ranges, stuff like that, and then save it back to the GRiSP board, and then the next time it will show up exactly as you want. And also we want to look into more higher level graphing libraries, because D3 is quite low level, so there may be a lot of effort to do all of this just straight in D3.
So for February right now, for the GRiSP project, we're already shipping the hardware since last year, and we're working on releasing the next version of the runtime, version 1.1, with the latest drivers and fixes. And so what we have working is Wi-Fi, W82 encryption, Erlang, or the latest version of Erlang is running with crypto, so you can do like HTTPS and other things. And we have all basic drivers kind of kitted, so we have the drivers for all the different ports on the GRiSP, and we are slowly working on adding like high-level drivers. So one example is for these temperature sensors. We have different P mods that we want to have drivers for, things like this. So we're part of a EU project called Lightcone, and it's kind of an Internet of Things project. They go into CRDTs, synchronization-free programming, hybrid gossip protocols, all with the purpose of improving edge computation. So by edge computation, we mean things which are close to the edge of networks. That means small devices out somewhere, and like your laptops, your iPhones, your mobiles, your GRiSP boards, whatever you have. So a way to like improve communication between such devices which are already close to each other without having to go to central servers all the time and synchronize. So we do lots of things there to improve, for example, Erlang distribution and things like this. So yeah, as I said before, we want more drivers, more high-level drivers. We're looking into pre-building the OTP or the Erlang VM that we use on the GRiSP board and the toolchain. So right now, if you want to create a GRiSP application, you would download our toolchain, you would compile it. This includes like GCC and other tools that is needed to compile, cross-compile software, any software, C software for the GRiSP architecture. And then with that, we then build Erlang using the Rebar plugin for GRiSP. So we build a specialized Erlang VM, including all the runtime drivers that we provide, and you can then add your own drivers, and then we can put this on the SD card. So we want to provide pre-compiled versions of all these things so that if you don't have any special needs, like you're fine with the GRiSP drivers that comes out of the box, you could just like download a package that's already built and deploy it directly instead of having to wait for all this compilation things when you set up a new project. As I mentioned in the line cone slide, we're working on fixing Erlang distribution. So Erlang distribution right now, it's a fully connected mesh. So if you add more nodes, all nodes have actually a TCP connection to every other node, which means like if you do an IoT project and you have like hundreds of GRiSP boards running in your big auditorium, for example, you would like quickly realize that the scale of this network wouldn't really work. So it's too many connections, too much traffic, and we want to make it more lightweight basically, and make it so that the connections are more dynamic, which means that if you have, for example, a smart conveyor belt with hundreds or thousands of Erlang nodes, we don't want to connect all of them to all other nodes. We want to like partition it a bit and be smart about where traffic goes and not to overload the whole network. So, yeah, that's it.
So this is GRiSP, that was the talk, and if you're interested in GRiSP and into getting, so there is the GRiSP website, grisp.org, and then all the source code is on GitHub at github.com/GRiSP, and there is also a free node channel. You can, if you have questions after this talk, I mean later when you're at home and you have more questions, then you can go to the free node channel, and then there is also a channel on the Erlang Slack. And also, if you're interested in getting a GRiSP board, you can get a 20% discount with the code Lambda 2018, all lowercase. And that was it. Thank you.
Thank you.
Yeah, thank you both. I really enjoyed the demo. So we have time for about 4 questions, I estimate.
Yes, hello. So if we have the application written Erlang as such for the home automation and just especially for the GRiSP board, and how do you think, how much effort do we need to deploy it also on some other ARM7, for example, for some other ARM7 board? Is it only to having the drivers, or some more effort will we need to put it on the another platform?
So it's definitely possible. The work you would need to do is, so we have a fork of OTP, of Erlang, where we did some adaptations. Most of the code is actually not in that fork, but in our GRiSP repository. So we have a build process where we build the Erlang VM, and during that process we copy in some extra code. So we override some files, then we copy in like the drivers, C files, and then we just run the normal Erlang compilation, cross-compiling it to our architecture. So if you had a different architecture, you would need to do 2 things. You would need to adapt the Erlang, the tweaks we've done to the Erlang VM, maybe change some files or set up some C code that you need for your specific platform. and you would need a toolchain for your platform. So you would need a compiler where you can compile C code. If you have those two things, then you could actually reuse most of what we've done and just replace those two parts and then target a different platform. And with the GRiSP initiative, we really want to do this. We want to, so the plugins and everything is set up for multiple platforms. And at the moment, we have one, or soon two, because we're doing some industrial platform as well for a customer. But there's nothing stopping you from like contributing a different platform or reusing the parts we've used and then just replacing what's specific for your platform. So that's completely doable.
Okay, thank you.
How does supporting multiple platforms connect to the Elixir Nerves project? Because in Nerves, you have the toolchain that supports multiple platforms out of the box. Would it be possible, for example, to create the modified Erlang VM plus the system as a target in Elixir Nerves project?
I think maybe yes. I haven't looked into Nerves so much in depth. So as I see it, there are two differences with Nerves and GRiSP. Let's say three if you count the hardware platform as well. So one difference is that they are targeting Linux systems. So we're talking Raspberry Pi, other systems which are actually way more powerful than the GRiSP board and powerful enough to run a normal OS and then put Erlang on top. And then they provide some system drivers to interface with hardware using, I don't know, the Raspberry Pi libraries and things like this. For GRiSP, we're actually targeting smaller, more low power, more efficient applications. So we don't have this operating system layer at all. So there's nothing you could share there to like you cannot put Linux drivers on this thing. You would actually have to take the C code and somehow integrate it with RTEMS and with Erlang VM. Another difference is that we want to provide, because we have the control over the hardware, we provide many more high-level drivers. And actually, right now, we have a complete set of drivers for all the kind of low-level interfaces on the board. And with Nerves, they are targeting much more like broader range of hardware. So I think they have a bit less like complete set of drivers for various pieces of hardware. So this is something like we see as a value that you should be able to buy one of these, start an Erlang project, and just immediately be able to use everything which is on your board. So this is one goal for us as well. There could be possibilities to share like more high-level infrastructure between the projects, but I'm not sure if it's worth it. We can definitely run Elixir on the GRiSP board because it's the Erlang VM. So I've done this. I've deployed an Elixir application without problems. We want to work on tooling. So we have a Rebar project. We want to work on tooling, which is a library that the Rebar plugin uses. And then we want to write an Elixir plugin for Mix as well that uses the same backend and can then deploy a Mix application directly to the GRiSP as well. So this is kind of how we see the world.
Thank you.